job. Yeah, so my title is a question, and that's the only thing that I want to leave it with it. So that what system primitives can get us to 1,000 times serverless AI inference? So I would argue that this wouldn't be the like a faster GPU or chip, like to easily give out like a 1,000 ton. I would argue that the answer could be the system software, but only if we can make it in the right architecture that compose like a layer of principal and efficient system primitives. So let me show you why. Okay. So let's start with like a very simple metric, like the investment in the cloud infrastructure. So this year we have around $600 billion of AI infrastructure this year, and we anticipate to head to around $5 trillion build out by 2030. And the hardware is super expensive, and it's also changing the architecture-wise, the H200, B200, and the Ruby 300, right? It's also changing a lot, like every 1 or 2 years. So, and where does this orders of magnitudes difference between the software performance come from, right? So, one example is the recent AMD effort try to optimize the DeepSeek V4 on the AMD MI355X chip, right? So the chip has been there for half a year or the 1 year, but then where the model coming in, right? It took like AMD almost like 2 months to optimize the performance over 100x. And this 100x actually is done purely at the software level. So basically, the chip remained the same. So basically, this actually means that there's so much huge potential that we can do from the software side. But actually, that 100x improvement is usually trapped. So I will argue that it's actually welded. Welded means that actually this 100x improvement is welded to one chip, a single chip, and one model, a single model. If you change either, and that performance is gone. That is actually what exactly serverless actually was initially proposed for, right? So if we can decouple the model from the hardware, and then we do that, and you get a whole list of the benefits, like we previously discussed about the no vendor lock-in, migrate workload, scale to zero, pack many model on shared GPU, paid only for useful work. And usually the price is not like simply a faster GPU kernel. It's like a more efficient system software, maybe as complex as a modern operating system, right? But if we can really do that, we can make the efficiency really portable across model and the chips. But actually, that's the reason why today we haven't really get that yet, right? So this is too good to be true in the current regard. And I observe two major reasons. One is that those reasons can be visualized on the two level in the entire computer architecture. In the level one, we have the heavy coupling between the model and the silicon, right? Like a very big, like trillion parameter MOE is usually hand-fitted to the GPU, like with the custom kernel implementation for different floating point precision, a different parallelism scheme, right? Even for training, post-training, inference, they all share very, very different parallelism scheme. And actually the memory layout is also very different, right? This actually makes the workload very hard to be portable. The level two is that the GPU has no usually operated. So even though today, right, GPU, the G means general purposes, but actually it has become like a highly AI specific, which means that many useful principles that we have been implemented for operating system are not there, right? So even though NVIDIA are doing their best to provide, for example, some virtual memory, some of the NPS services, right? But because the architectures change significantly over generations, so usually every time where we enable that, that usually means like huge performance lost. So this actually could mean that, so if we are running some high concurrency services, right? Unlike the old days in the GPU land, in the CPU land, a GPU can't natively pause or move or share a running model state. Okay, but the people may argue that, right? So VLM and SGLang, they already run many model on very hardware, but this is true only functionally because running doesn't mean that running efficiently, right? Especially under the sharing, migration, and the elasticity circumstances, right? This actually could be shown by why AMD still need to spend almost 1 or 2 months to optimize the model performance. So yeah, so actually this gap really motivates this entire line of work and that I will show in this talk. Well, so basically the methodology is very simple. So we actually borrow from how people have been designing operating system in the last several decades. And operating system by principle, it will try to decouple application from the hardware through like a very thin layer of efficient primitives, right? Like virtual memory abstraction, file system abstraction. So, and can we actually do the same for service AI? But we don't really want to repeat all the same principle again, right? For AI, because simply repeat the same principle wouldn't really create any novelty. Or so this actually means that the principle we are going to develop may look similar, but they shouldn't be identical. Okay, so to really look that, I will argue that the principle we are going to develop for service AI need to be need to be AI native. At the level one, it needs to be AI hardware native, which means that the service AI software system need to exploit the GPU and also other AI accelerator, memory hierarchy characteristics, compute, and also their networking characteristics, right? So this must be designed as the native level. The other one is that we would no longer focus on general purpose cloud application, right? So many data center in this day, especially for GPU cluster, they are built only for serving AI workload, right? This actually means that the software stack itself can be AI model aware or AI model native. This actually will unlock some of the optimization actually, which wouldn't be possible if we cannot make like a valid assumption about the workload. For example, how the sparsity of the mixture of expert model would look like, how the sequence actually are being computed using preview and the decode. So for example, right? And in the end, we want to distill each gain of this principle into a system primitive so that we can composing primitives as a stack. So in the end, all the benefit they can be multiplied, not only about overlapped. So like a very interesting analogy can be observed in the AI-specific computer architecture, right? In the last 10 years, actually GPU architecture performance-wise has been evolving for around 1000x. So the 1000x improvement from the GPU architecture not only come from that they are using like a finer process node from TSMC, it's also because that they are embracing about lower precision floating point. They are also adding more complex instruction set. They are also adding some hardware instruction for data movement, right? That everything combined in a very coherent way actually can give a GPU a boost for 1000x in 5 to 10 years, even though the process node only goes around 3 to 4 times. Another successful analogy can be seen in the AI-specific programming languages, right? We have been seeing the Triton programming language, right, has been very powerful, even though it's like pure Python. But it's actually much faster, even compared to some C programming language, if they are not bearing AI-specific computation requirement in mind. And another question is that why not we cannot build an AI-specific distributed operating system? So we can sacrifice some of the general purposes design assumption, but now today many classes they are only designed for AI, right? And the service actually maybe can be that OS for the AI compute in the future. So I will actually demonstrate how this design principle has been implemented in the last 2 years. And the one is the service LLM. It was published in in OCDI 24. So it implement the principle one, how to make like a service software stack to be AI hardware native so that we can address the code style issue that's very common in many serverless compute stack. The other one is the BatchGen. I will demonstrate that how we can exploit the memory sparsity and the sequence compute structure so that we can build an efficient compute engine for inference. And actually, both of the system, because we are designed by having the principal primitive in mind, so actually they can be combined to give you over 100 times improvement. So both of the system, they are highly modular. They are not monolithic design. So let me quickly start with the service LLM. So usually in a GPU cluster, we often need to start AI services on demand. And so this is very common in an auto scaling scenario. So, but the problem is that the checkpoint is very big, right? So even though this result has been measured around 2 years ago, so even though during that time, right, so Llama 2 model has around 130 gigabyte of the checkpoint, and today, if we are talking about like a MOE with a trillions of parameter, this number can go up to around several terabytes, right? Even though with like today it's already relatively smaller model, it take around like a fairly long time, right, for the inference cluster to auto scale a model. And this actually can put, and this is because so the large checkpoint can prolong the model download, and also the heavy driver and the inference runtime design also increasing the loading time. The driver, I mean the CUDA driver also, yeah. And also we have some complex inference process also causing some unpredictable time. So basically the auto scaling latency actually is the key problem here. But actually, if we directly borrow some of the principle we have been developing for cloud computing, usually we will try to oversubscribing server, but the GPU server, they are so expensive, so oversubscribing wouldn't be very economic viable in the long term. We might also have the DRAM cache, but the DRAM cache is also increasing in price. And also because the model itself is already quite big, like several terabytes. So actually DRAM also wouldn't be alone sufficient. We might also have a additional like a storage server, but actually networking bandwidth is also quite expensive, even compared to GPU. So actually what bring into our attention is that, so usually for GPU server, if you buy it, they will actually come by default, give you like a sufficient DRAM and SSD on the CPU side. Even though for today's like upcoming GPU architecture, like the NVIDIA super chip, right? Like the Grace Hopper architecture or the Grace Blackwell architecture, they even can give you some LPDDR, lower power DDR, so memory just sit alongside with the HBM. This actually means that for many modern GPU server, they have like a very rich and spacious memory local hierarchy there. So this actually motivates us that, so if we really want to have like a very fast auto scaling, we should unlock these idle resources that to benefit the GPU for sharing them. So, and actually, I wouldn't really go into the detail since this is like a keynote level. So there are like two key observation we are leveraging for the AI workload to make this happen. One is that, so an AI checkpoint actually is a read intensive and the written once data object. So we wouldn't really need to assume it's like a general purpose file, right? So if we know the workload access pattern, we can make some design assumption that can make it really fast. Also, the checkpoint format itself can be effectively indexable. Okay, this actually could mean that some of the loading of optimization can be made here, but it can work very well in these circumstances. This motivates us to design a loading optimized checkpoint format. Okay, then we keep it as a chunk-based pin memory in the DRAM and also the SSD. The other thing is that, So usually you have like a multiple memory hierarchy. We can actually build like a multi-tier loading pipeline that uh, we can try to streaming the checkpoint from the farthest tier into the GPU. And this pipelining could be actually make it quite effective based on two observations. One observation is that usually where we try to schedule the inference request in a big AI cluster, usually there's like a very good chance you can somehow overlapping the preloading of the checkpoint and also the inference because we know the workload quite well. Secondly, is that usually the checkpoint they can be further partitioned, right? So they can be actually keep some chunk onto different tier, and where we are loading it into the GPU, so GPU can actually even live with some partial checkpoint can already start the inference. So this actually is only possible with the AI compute because the layer by layer architecture in the neural network. Okay, and if we can really do that, we can boost the performance by around 5 to 8x for the inference latency, for the auto-scaling latency. Another thing is that we also introduced like one key concept. It's called live migration. So live migration has been very successful for the virtual machine land, but actually before this paper, there's no such a concept for the inference. And then actually we identified that the live migration actually could be quite useful for the inference case. But actually live migration, even though they have like a huge application scenario, but how to do live migration, right? And very obvious choice, if we directly borrow from the CPU land design, is that let's try to checkpoint the entire state of the inference process, right? And then let's migrate the state from machine one to machine two, and then let's resume the entire state and then run it. But very unfortunately for the GPU, usually the KV cache is a state. And actually, if we are running with very long sequence compute, that KV cache itself can be around tens of gigabytes. And then we make a key observation for the AI workload because GPU itself is like heavily optimized for compute. So sometimes actually recompute the KV cache is even much faster compared to shipping the KV cache entirely over the network. This actually makes the recomputation of the KV cache actually can be dependent on the GPU architecture as long as the length of the sequence, right? So the key observation here is that for any of these key system design principle that we made, especially for live migration, it need to be very well aware of the GPU architecture, right? The compute to memory ratio, the compute to network ratio, and only with those, right, we can make the most efficient design. If we combine the live migration, the primitive as well as the fast loading primitive I just showed to you, we can together reach around 10x faster cold start compared to some industry solution at the time that was Ray or Kubernetes, even though they have been optimized for the GPU land. Well, I have okay. So basically, I have talked about so fast loading and the live migration. There's another workload is also quite growing. It's called the batch inference. So basically, the batch inference is like a compute paradigm typically used in the model evaluation, right? You have like a checkpoint coming in, you have like a very big data set, like maybe have around millions of sequence, and then you need to validate the entire model performance. You need to wait until the very last sequence to finish until you can return the answer. So that's why the entire batch needs. So here we no longer optimize the interactive inference latency anymore. We care more about the batch completion time. And this scenario is also very common in the reinforcement learning scenario, where the rollout phase itself is also a batch inference scenario. The same for some other like synthetic data generation. Okay, so we are actually seeing that there's a fast increasing number of GPU being deployed for the batch inference, even though some tens of thousands in some frontier AI lab. Okay, but then today, if we are talking about batch inference, the most straightforward way is to directly use interactive serving engine like the Epsilon and the VLM to really do that. But very unfortunately, SGLang and the VLLM, they are designed for optimize for the time to first token and also time per output token, right? So that's why they always optimize for the lower latency. But on the other hand, as you can see here in the batch completion scenario, we no longer really care about like the latency of a single sequence, right? As long as there's some straggler right there, we always only care about the entire batch completion time here. And I will argue that this shift between latency to throughput orientation performance metric may actually completely shape about how the best inference engine can be designed in this regard. Yeah, so, and actually, if we look into how today's batch inference, right, we actually see that MOE, even though it's actually quite big, and also we have a lot of sequence, the performance actually is quite bad. So usually MOE will have like a router and many experts, right? We have been seeing DeepSeek, Kimi, GPT, Gemini, JLN, and Rapid, they're all using MOE model. But actually, even though you might have a lot of token, after the attention module, but after the router, each expert only receive like a smaller batch of token. If we're actually doing some benchmarking using modern GPU like the H200 or the H20, right? As you can see here, so usually, even though for the preview, which is supposed to be compute bound, so both SGLang and VR, even though we have been heavily optimized it together with our industry collaborator, it is still operating under the compute underutilization land. For the decoding, this is even far more the case. Okay, so BatchGen is a system that we design. We can actually raise this utilization actually quite significantly, which I will show you how. Okay, so but actually, what is the root cause? Why SGLang and VLLM actually suffer from this? And that is because there's always a price we make the system optimized for a single scenario, which means that the interactive mode, right? So usually, if you really care about the latency, so usually they will ping the sequence, right, to a GPU until it's done. So the entire forward pass will be atomic, even though you can do continuous batching, but this actually will only allow a new sequence to join the computation. It doesn't mean that you can actually change the binding between the sequence and the GPU during runtime. And people are doing preview and the decode disaggregation and also attention and expert disaggregation, but this can only relax the phase placement. It wouldn't really change about the binding scheduling decision. There are two major consequences here. It actually means that, so even though you can observe that the expert doesn't have sufficient batch, or you have like a long tail problem, but you can't really pause the mid pass to regroup token into a larger expert batch. So, and this actually is quite important to actually to save the starving experts. And then you also can't really move or repetition a straggler. And this actually make the heavy tail really hard to be addressed. And our key observation here, especially for the AI workload, is that actually the process of a sequence compute can be like a perfect model for event-driven coroutine, right? If you, so here, if you have like a multiple sequence, you have a model, you have some layer, you have some boundary. So usually the module boundary can be a very natural yield point of the sequence compute, no matter they are running at the preview mode or the decode mode. And actually during the preview and the decode, and each sequence state actually is quite compact, because even though the KV cache can be quite big as a total, but for each sequence, actually it can be quite compact and actually can be migratable because you only need to migrate the KV cache. All the model weights, they are being shared. And also the scheduling overhead, if you do dynamic binding between sequence and the GPU, because today we care about batch completion end-to-end time. We no longer care about the token per like the TT, the decoding token latency, right? So this small actual scheduling overhead can be naturally hidden in the batch completion. And this actually motivates us to have propose a coroutine runtime for implement this. Like a powerful analogy can be observed in the early days where we are designing the web server So in the early days, we have the Apache server. So we have the thread and the per request mode, and then later we move to the Nginx, which can be make the event driven. And now we also need to implement the same design paradigm shift for the GPU-based inference engine. And I also think this actually fits the topic of the conference quite well, right? The depth, right? The, the event-driven streaming processing engine, okay? I will actually quickly talk about this. So we introduced 4 key system primitives. One is called YALT. The other one is called combine. We can actually, so that we can combine the token for the starving experts. And then we can do partition. If we found out one sequence becomes the straggler, we can partition it so that we can enjoy more tensor parallelism. And then we could even migrate to some less busy GPU in this regard. So basically, and all the 4 primitives actually we have implemented into a single engine. Okay, let's talk about the results, right? So if we run the DeepSeek R1 full model on a cluster with 128 GPU, so usually you can have around 1.6x performance improvement. Today, actually, we also doing some better work for our kernel implementation, and this result can be reached to around 2x. The other thing to be really noticed that is the memory efficiency of this engine, because as you can see here, right, we are actually a coroutine engine. So most of the KV cache, they can be very efficiently hosted in the hosted DRAM. So this actually means that we have like some much more natural way we can get around of the GPU memory capacity limit. So basically, we are the only system that can run like MOE with over 1 trillion parameter that are on like a one single 8 GPU server, where all the other engine they need at least 2 to 3 server. Another big plus, actually, we received the feedback from our industry partner is that, so today for many industry inference cluster, they must have some very fragile static resource disaggregation, like the prefill and the decode disaggregation, but actually deploy and hard code it into the cluster. But actually in the production, prefill and the decode ratio, they will dynamic change, especially for agentic workload. But as you can see here, by having the decode routing engine, right, the disaggregation of the prefill and the decode become a task, and that will turn into a runtime scheduling problem. So that actually means that no matter you have like a more prefill heavy or decode heavy, our software and the scheduler can always react to it, right? Where in the hardware partitioning approach, you can never really react to it very adaptively. Okay, so and hopefully by showing you how BatchGen and the ServerlessLLM, I show several primitives that we can combine that can really give you around 10 to 100x improvement. But where could be the missing 10x can come from? There's like one frontier I can see is the heterogeneous chip, right? Today, as we can see, the chip is getting diversified. We have the SRAM oriented computing platform like the Grok LPU, the Cerberus WSE, and also the Grok Core or many others, right? So we also have the GPU architecture like the NVIDIA AMD TPU, and Amazon Trainium and many others. We also have the DRAM-centric computing platform like those from the TestTorrent. They all fit different good needs, okay? And the serverless actually, by design, can be the key to hide the diversity. So basically, last year in OSDI, we showed that if we can have some system primitive for wafer scale computing engine, you can have around 10x faster decoding. But today, to use the wafer scale engine, the user must hardcode many kernel, and we hope the future serverless actually can hide that complexity. The other thing is the agentic and the long sequence and the multimodality workload can emerge, right? And the service must be natively optimized for that, especially for agentic, right? So because some of the lesson we learned from the old service compute is that porting the workload is always very hard. But today, with the AI agent help, right? Even so many GPU kernel today are written by AI agent directly. This actually means that by porting some legacy application onto the newer one wouldn't be that difficult. Okay, so and hopefully by opening these 2 new frontier, right, we can have the game that can multiply through the life cycle, hardware, and the workload, and we can eventually reach around the 1000x improvement. Okay, thank you. Yeah, that's all for my keynote. Thank you so much.
Thank you very much, Luo. do we have questions about the keynote? Please.
I have one also.
Yeah, go ahead.
Yeah, no, congratulations, Lou. It's impressive. And the title is ultra ambitious. I mean, 1000x improvement. It's amazing. I mean, it's what you presented. It's really nice. No, my question here is about, I mean, this kind of extreme optimization. I mean, the big hyperscalers like Google or OpenAI, they will be, of course, optimizing like crazy how they serve AI, how they use these LLMs. I mean, the rest of us can do these kind of things. I mean, if you can really accelerate by 1,000, this is really a cutting edge research activity. So not everybody is at the level of using this, or people can just take your open source contributions and obtain this kind of extreme acceleration.
Yeah, I see. I see. So usually this 1000x is not coming from a single layer, as I mentioned. It comes from multiple layer, right? Like the co-star, the inference, like especially the batch inference, and the later can come from some um, specialized hardware, like the wafer scale engine on the NVIDIA LPU cluster. Usually this 1000x will be possible for a single important scenario of AI, like the batch inference. But I wouldn't argue that this 1000x can be so pervasively easily applicable to all the AI workload. Because in the AI workload, we have so many different AI workload, right? Like the post-training, pre-training. For the inference, we have the agentic, long sequence, multimodal data, right? But the good news is that each of these kinds of AI workload itself, we already have important use cases. For this important use case, we can still have this layer of the primitive that we can combine and hopefully to reach that higher level of the improvement. And also, regarding to your question about, it seems like only the hyperscaler has all the elements that can do this kind of the research, right? So this might be the case in the like several years ago, but today, as we can also tell, right? So AI workload is getting much more agentic, which means that you have AI model to interact with many operating system key module, right? Because today AI agent now start to write data directly to file system, right? Calling some of the Linux sandbox or tools, right? Actually, this is becoming a key bottleneck at this moment. So this doesn't really require a very big GPU cluster. So for this kind of research, actually, I think we can still certainly do it in a very pure academic setting. Uh, and also for two examples show here, like wafer LN, yes, of course, we need to get access to some advanced chip. So this would be only possible if we can collaborate with the supercomputing team right here, maybe in the Europe. But for the context pilot, the other work is pure working at the context level, context management. Okay, by doing that, we also really don't need like a very advanced GPU. I think it's like a case by case. We need to figure out like a target, like a workload scenario, and usually there's a chance we can reach that level. Yeah.
Thanks a lot.
Are there any additional questions?
Alex,
yes, go ahead.
We have questions on Discord. Should I relay it? Or
yeah, please relay. We can hear you, or ask somebody to ask directly. Go ahead.
What did you say is the biggest bottleneck for serverless AI workloads from an hardware standpoint?
There's an echo in the room, so that's why I cannot hear the question very clearly.
Can you hear now?
Yes.
What would you say is the biggest bottleneck for serverless AI workloads from a hardware standpoint?
I will argue that so right now I can I can only share some of my personal experience. Okay, so basically, so OpenAI is using Triton. Triton is like a programming language dedicated for AI programming. So today, actually, Triton has been quite successful in supporting heterogeneous chips, right? So we already see Triton supporting NVIDIA GPU, AMD GPU, and hopefully they can also support the Google TPU soon, right? So basically, this actually could mean that some of the at the programming side, this can be unified, and this will be like a very good news for serverless because this actually means some of the kernel implementation can be unified. But still, Triton in the future, I will anticipate that it will expose like a more configuration allowing the software to tune, right? So this actually means that even though at the program abstraction level, it has been unified, but the software itself need to have like a very strong cost model that you can actually predict under what configuration the kernel can give you good performance, right? And then so the other one is the verification. One of the things that prevent AI agent to directly write system level code is because there's no clear signal if the performance of the resulting system code is good or bad. I will also argue that the verification loop is also getting very important. So by doing that, we can learn many things from operating system research community in the past decade. For example, like the eBPF, for example, could be like a very good way to profile and debugging the performance bottleneck, right? So I will argue that the verification loop is also a key thing, yeah, that to work on. And it has become a key bottleneck. Yeah.
Thank you. We have another question, Alex. Can I?
Yes, go ahead. Yes, go ahead.
So confidentiality, for instance, as given by trusted execution engines, could it slow down your plan towards the 1,000 times speed up? What's your plan there?
You mean confidential engine?
Confidential computing.
Yeah. So confidential, I think. So I think different from the old days where we have to do a lot of research for the Intel TE, right? So right now the GPU is especially for the data center grade GPU from NVIDIA, they already provide the TE support by default. So it is similar to how AMD provide the computational computing for the so that the application doesn't need to do anything for that. But I think for confidential computing, if we look beyond that, so today we also have this very strong concern about the privacy, right? So if we share some of the context with the API provider, it's also very likely we might disclose some of our key skills, and in the end we might be replaced. All right. So I will argue that